Okay, moving on in Unit 2, we're going to be looking at how we measure numbers and use significant figures. Sometimes significant figures is abbreviated as sig figs, and so you'll see me use that a few times because I'll probably slip up and just call it sig figs, but that just means significant figures. So in the last video, we talked about how length is measured and that we use centimeters or meters because we're using the metric system as scientists. So length is measured by observing the marked lines at the end of the ruler. The last digit in your measurement is an estimate, and that's obtained by visually dividing the space between those marked lines. And so we're going to talk about the difference in like generalization versus significant figures or sig figs, right? So the goal for this is to identify the number as that's being measured as exact, or if we can determine the number of significant figures from that measured number. Okay, so it's more like, is it an estimate or is it actually exact? So measured numbers are the numbers that are obtained when you measure quantities such as your height, your weight, or temperature. To write a measured number, you're going to observe the numerical value of the marked lines, you're going to estimate the value of the number between the marks, and then you're going to use the estimated number as the final number in your measured number. Okay. An example of this is if we're using different rulers, they can have different gradations and they can be a little bit more accurate or less accurate, and this is an example of that. So the lengths of the objects are measured as in A here. We can see that it's between 4 and 5. We can roughly say it's 4.5 centimeters. Where if we use B, you can see that there's millimeter markings, not just the centimeter markings. So we can get a little bit more of an accurate measurement. And you can see that it's 4.5 and a little bit more, not quite to 6. So it's 4.55. Okay. Where, again, we go back to a larger, just not as detailed scale. And then that just shows you that that's going to be about 3 centimeters. Okay. So in a measured number, the significant figures or sig figs are all the digits including the estimated digit. And so these sig figs are used to represent the amount of the error associated with the measurement. So all non-zero digits and zeros between the digits count, not zeros that act as placeholders before the digits. And I know that might sound a little bit confusing right now, but we're going to talk about it, okay? And also we're going to talk about the zeros at the end of the decimal number. So this is going to drill into that core chemistry skill of counting your sig figs or your significant figures. So a number is a significant figure if it has if it is or has the following. And so you can see that a number is a significant figure if it is not a zero, if it is a zero between non-zero digits, so 205, that zero counts. If it's a zero at the end of a decimal, 50.0, 25.0, that counts. If it is the coefficients of a number written in the scientific notation, for instance, 5.70 times 10 to the negative 3. Remember, we'd have to move the decimal point 3 times to the left, okay? And so if we look at this, how many sig figs would we have? Well, 4.5 grams would be 2. 1.22.35, that's 3 on the left, 2 on the right. That gives you 5 number of sig figs. This 205 is 1, 2, 3 numbers, so that gives you 3. This one, 5.008, again, everything counts, so that would give you 4, etc. Okay, so you can see that those are when they count. A zero is not significant if it is at the beginning of the decimal number. Okay, so this one, you see how it's 0.0004 seconds. That's only one sig fig because all those zeros, they're just like a placeholder. Okay, 0.075 is only 2 because those zeros before are just, again, placeholders. Or if it's, again, used as a placeholder in a large number without a decimal point. So 850,000 meters, you would only have 2 sig figs. So I know that this gets a little bit sneaky, so take a second to write that down and just kind of remember this figure, and we're going to do a couple practices. Okay? So when one or more zeros in a large number are significant, they're shown clearly by writing the number in scientific notation. Okay, we talked about scientific notation a couple of lectures ago, so this is where it's coming back in and tying together. So in this book, we placed a decimal point after a significant zero at the end of a number. For example, if only the first zero in the measurement, 300 meters, is significant, then the measurement would be written as 3.0 times 10 to the 2 meters. Okay, because remember, we'd move that decimal point 2 points to the left, so that'd give us the 10 to the second power. Okay, okay. So, moving on, zeros at the end of the large standard numbers without a decimal point are not significant. So again, this is moving off of that table that we were just talking about. 400,000 grams is written with one significant figure as 4 times 10 to the 5th grams because there's no specific identity, if you will, in these numbers. It's just 4 times 10 to the 5, right? So this one, again, those zeros are just placeholders. So this would be two significant figures, 8.5 times 10 to the 5, because that tells you how many times you're going to be moving that decimal point. Zeros at the beginning are used again as placeholders and they're not significant. So do you see how if it's like not really needed, it's not going to be significant. But if it's telling you like 4.067, then that zero would be significant. But other than that, if it's just telling you how many times to move your decimal point, then that's when it's not going to really be significant. Okay, so here's an example. If we identify the significant and non-significant zeros in each of the following numbers and write each number in the correct scientific notation. Okay, so I'll give you 1 sec to do that. Take a sip of my orange juice. All right. So for answer A, the zeros preceding the 2, again, remember they're not significant. Okay, and remember that 10 to the minus 3, that tells us that we would 1, 2, 3. We would be moving that decimal point 3 times to the right. So that's why it would be 2.650 times 10 to the 3. So that gives us 1, 2, 3, 4 significant figures because these two zeros again are just placeholders. They're telling us how far to move the decimal point. The digits 2, 6, and 5 are significant, and the 0 in the last decimal place again is going to be significant because that's part of the larger number. Moving on to B, 43.026 grams. When we write that in scientific notation, we move the decimal point one point, so that's 10 to the first power. And then the zeros between the non-zero digits. Sometimes I wonder if I'm speaking English, but really it makes sense, right? So the zeros between the non-zero digits or at the end of them are significant. Okay, so that would give us 5. 1, 2, 3, 4, 5. You can see that again here. 1, 2, 3, 4, 5. Because that zero is in the middle, he's very important. Okay. For this guy, for C, when we take this big 1 million number and we write it as, into the 10th power, then this would be 1, 2, 3, 4 significant figures because these little zeros are non-significant. Okay. So yeah, so you can see that it's just kind of like if the zeros are placeholders, they're really not important enough to call them significant. They're there because they make the number pretty, and when we're not writing in scientific notation, we need them there. But other than that, when we write them in scientific notation, they would just be clutter. Moving on to what an exact number is. Exact numbers are not measured and they do not have a limited number of significant figures. They also do not affect the number of significant figures in a calculated answer. So these would be numbers that are obtained by counting. For instance, I love cookies. I love insomnia cookies, right? I could eat 8 insomnia cookies. That is an exact number. It can be used in definitions that compare two units in the same measuring system. So 6 eggs is an exact number. 1 quart is the equivalent of 4 cups. That's an exact measure. 1 kilogram is the equivalent of 1,000 grams. That is an exact measure. Okay, so here are some other examples where 8 donuts right? 2 baseballs, 5 capsules, again, liters to milliliters, or, feet to inches. These are all exact numbers. So, doing another little study check for you guys. Identify the numbers below as measured as exact and give the number of sig figs in each of the measured numbers. So, take a second to do that. I'm going to see if my cat would come up and play. Okay, so 3 coins, again, is going to be a counting number, okay? So that is therefore an exact number. I have exactly 3 coins, okay? The number, or the diameter of a circle, is 7.902 centimeters. This is a measured number, and the 0 is significant because, again, it's in the middle. It's not just a placeholder. So it contains 4 significant figures. And then 60 minutes is exactly an hour by definition. Okay. So when we move on and we use this in calculations, a calculator is very helpful in working problems and doing calculations faster. Yes, we can do them in our head. When I was growing up, my teachers always said, "You're not always going to have a calculator on hand." Well, you know what? I do. So, now we do, but of course, back then we did not. Okay. So a calculator is helpful in working problems and doing calculations faster. And so our learning goal for this part of this lecture is going to be adjusting calculated answers to give to give the correct numbers of significant figures. Okay, so we're going to show you when we round and when we don't. So our rules for rounding off. If the first digit to be dropped is 4 or less, then it and all the following digits are dropped from the number. Where if the first digit to be dropped is 5 or greater, then the last retained digit is increased by 1. Think of rounding a grade, right? If you get 3.49, hopefully your teacher would round that up to, a 5, or 3.49, 3.5, right? Where if you get, we'll do examples, but basically it's how we're going to be rounding off, okay? So this one here, the original number is 8.4234. If we want 3 significant figures, we would have 1, 2, 3, and we would drop 3, 4. So it would, again, since it's under 5, that would stay a 2. Okay, if it was 8.425, then that 2 would make it up to a 3. Okay, but again, we're going to go through some examples. So if we want 3 sig figs, this original number of 8.4234 would be rounded to 8.42, and we drop those last 2 3/4. If we wanted only 2 sig figs, then that would be calculated to be 8.4. Now, if we look at 14.78 and we only want 3 sig figs, do you see how this 8 is bigger than 5? So that means that this 7 is going to become an 8. So 14.8. You're going to drop the 80 because the last digit has to retain digit by 1. Okay. But if we want to just round it up to 2 significant figures, well, 14.8, that 0.8 was above 5, so then that would round it up, and then that gives us 15. Okay, we would drop that 0.780, and since this is above 5, it would increase that last retained digit, which was 4 in the original here. It would increase it by 1. So again, this is just your rounding rules, okay? If you think of them as grades and you think of if your teacher would curve your grade or round it up, it makes a lot more sense than just looking at numbers on a paper. Okay, if we look at this last one, 3,256. So if we are going to 3 sig figs, remember that last 0 is just kind of a placeholder. So what's going to happen is we're going to drop it, but since it was 6, that means that it was above 5, so it's going to round that 5 up to a 6. So that becomes 3,260, okay? Where if we want 2 sig figs, then again, this 5 is 5 or bigger, right? And so that means that we'd have to increase that 2 to a 3. So we dropped the 5, 6 and increased it by 1 because again, it's bigger than 5. So again, just think of it as like rounding grades, and it makes a lot more sense. So let's do a little study check now. Write the correct value when 3.1457 grams is rounded to either 3 sig figs or 2 sig figs. Okay, so take a second to think about that. Okay, so when we take the first one, right, when it's rounded to each of the following, so 3.1457 to 3 significant figures, we would want to drop the last 2, and since this last one is 5, we'd end up having to increase the third one here by 1. Okay, so it would become 3.15. If this 5 was a 4, then it would stay at 3.14. But since this last number here is above 5, that means that we have to bump the guy up above, before him up 1. Okay. To round 3.1457 grams to 2 sig figs, then we're going to drop the final digits, okay, and we'd be ending up with 3.1. And since this next number is 4, 4 is below 5, and so that's not going to bump us up to round it up. So he's going to stay rounded down. And so our final answer would be 3.1 grams. Okay. Hope that's helpful for you guys. Using this and moving on a little bit more for multiplication, division, and measured numbers. In multiplication or division, the final answer is written so that it has the same number of significant figures as the measurement with the fewest significant figures. Again, sometimes I don't think I speak in English, but I really do. Okay, so basically we have to look at both numbers and figure out which one has the smallest amount of significant figures. So this one has 4 significant figures, this one has 2, so that means that we can only have 2 significant figures for the final result. So if we take 2.466 centimeters and we times it by 0.3 centimeters, then that would give you 8.631 would be what your calculator would say. But the exact correct answer, remember we can only go by the fewest number of sig figs, and this one is 2, and so we would have to drop off the 3, 1, and since the 3 is less than a 5, the 6 stays a 6, but if the 3 was a 5, then we'd have to round that 6 up to a 7. Okay, so then with the 2 significant figures, that gives us 8.6 centimeters squared, because we have centimeter there, centimeters there, so that gives us a centimeter squared final denotation. Okay, and so multiplying 4 sig figs by 2 sig figs gives us an example or an answer with the 2 significant figures, again because we go by the lowest significant figure number. And so this is what we're doing to use significant figures in calculations. Okay. We can use this with multiplying and dividing. Okay, so again, we're going to multiply and divide the following measured numbers: 21.5 centimeters times 0.030 centimeters divided by 1.88 centimeters. So using a calculator, we do the top first and then the bottom. Compare the amount of sig figs. We see that we only have 2 sig figs. That's our lowest number from this number here, right? So when we end up getting the calculator's display, it's really long, but to make it the most correct, we can only use 2 significant figures. So then 3.43, the 3 is less than a 5, so that gives us 3.4. If this 3 here was 5 or above, the answer would be 3.5. Okay, so again, multiplying 3 significant figures by 2 significant figures, 2 is the smallest number of sig figs, so that's why we can only report our answers in 2 sig figs. Okay. All right, so when do we add significant zeros? So when the calculator display contains fewer significant figures than needed, then we have to add 1 or more significant figures to equal it out and get the correct number of significant figures. Scientists can be very picky, okay? So if we look at this equation, okay, we have 6 grams divided by 2 grams, and so if we use a calculator, 6 divided by 2 gives us 3. But when we look at the significant figures, right, 6.0, would be the two significant figures, which is the least amount of significant figures. And so we actually have to make this 3 solid a 2 sig fig number or answer. So then that would give you the 3.0 grams. Okay, so we just have to keep it nice and uniform. So here is another example for you to do. Okay, so perform the following calculation of the measured numbers, giving the answer in the correct number of sig figs. Okay, so work on this guy for a second. I guess you could pause me too. Instead of watching me drink my orange juice. Okay, so again, what would we do? Top one first, so 5.00 times 3.48, because centimeters are the same, so we can directly multiply them. Divide it by 2, okay, and that gives you 8.52. But when we look at this number here, our lowest number of significant figures would be 2, so we'd have to needs to have the 2 sig figs. Okay, so then that would be 8.5. I don't know why they didn't change that. All right. So when we add and subtract with the significant figures, again, same rules apply. In addition to subtraction, the final answer is written so that it has the same number of decimal places as the measurement with the fewest decimal places. I tell you, I don't know who mathematicians, like what they like to do that besides torture people, right? To come up with these rules. But they do. So we have to figure or follow them. So an example here, if we add the following numbers, 2.012 plus 61.09 plus 3.0, you can see that this goes out to the thousands, this goes out to the hundredths, the tenths, so this would be the calculator display, but since we have to pick the lowest guy with only tenths, that would be our answer because 6.10, 0 is less than 5, so the 1 stays 1. If the 0 was bigger than 5, then that 1 would round up to a 2. Okay, so the same rules apply. All right, so example 2 here is going to be subtract the following measured numbers. Again, 65.02 goes to the hundredths, 3.0 goes to the tenth. This is what the calculator displays. This is the lowest common denominator is tenths, so then we can only answer it in tenths. Okay, and since this 9 here is above 5, that's why we round this 0 up to a 1. This guy carries over. So that's why we get the 62.1. Okay, we're almost done, guys. All right, so again here, add the following measured numbers. I'll give you a sec. Okay. All right, so again, the first number goes to the thousands, second one goes to the tenths. Calculator display gives you out to the thousands, but the lowest common denominator guy would be here in the tenth. And so since this 0 here is the 0, which is less than 5, the 4 gets to stay a 4. If this 0 was above 5, the 4 would go up to a 5. So I hope that that was somewhat interesting, not super confusing, but you can rewatch, slow down, and like I said, I don't know why there were a couple little errors, but we got it. Sophie, you're gonna say hi? You gonna say hi? Come here. So you guys get to meet my cat. So Sophie says hello. She doesn't want to be up here. All right. You guys have a great day, and we'll see you in the next video. Thanks.